This is an introductory video to Lex and Yacc, two powerful tools often used together to conduct lexical and syntactic analysis. We'll introduce Lex and Yacc in the context of compilers, but of course you can use it in many different circumstances that needs language processing. Let's say, theoretically speaking, you're a student of computer science, and one day you had the bright idea to build a programming language C, except with all the keywords replaced with the initials of your professors. However, after meticulously rewriting the file in your new language, you will need a compiler that analyzes the new syntax, and you have no idea what to do. You know how to code a basic scanner using the language like Python, but you have no idea how to parse these inputs. As your billion-dollar idea is falling apart right in front of your eyes, you thought to yourself, if only I knew Lex and Yacc, then I will be able to perform syntactic analysis without any problems. Lex, known as the lexical analyzer or scanner, lexer, or tokenizer, provides a standard way to process your input file into a stream of tokens for your parser. This is an example of a lexer that scans a subset of the Java syntax. A few things to notice here. Each line is a regex rule for a token. Inside the parentheses are C code. You can write any amount of normal C code inside them. These return statements will pass these pre-declared tokens to the parser. These rules here are not just normal text, but rather regex expressions that matches for the exact strings from the input file. Now notice the order of the regex rules. The priority goes from top to bottom, where these comment statements will be matched first, then these keywords, and lastly the literals and the variable names. In practice, Lex will scan the input file and try to match each rule one by one until it finds an appropriate rule to return, and it will continue to do so until it scans through the entire file. Unlike the keywords, the contents of literals and variables matter, so we need to store them before returning the tokens by attaching them in the struct so we can access them later in Yacc. In comparison, Lex tends to be pretty straightforward, and Yacc is where the complexity kicks in. Yacc, also known as yet another compiler, the parser grammar handles the context-free grammar portion of the compiler. We'll talk about how to understand the product rules of Yacc and how our code will interact with these grammar rules. But we'll first have to learn the basics of programming language design. We can understand what a language is by defining and using regular expressions. For an easy example, L is a language that accepts the string CDE. If the input is CDE, then we say the input string is accepted by language L. If not, it's rejected by language L. To further define the grammar of a language, we use production rules. This production rule here means given starting symbol A, it can turn into symbols C and B in that order. This sequence shows you how to go from the starting symbol A and apply the production rules to get the accepted string of your language. Symbols are either of two types, terminals or non-terminals. Terminals are the basic elements of the programming language, like keywords, variable names, and punctuations. They also can not derive into other symbols. In other words, they cannot appear on the left side of a production rule. Non-terminals are symbols used to define the structure of grammar. They can appear on both sides of the production rules and can turn into other non-terminals and terminals. At the end of grammar parsing, all of your non-terminals should derive into terminals, or else you should throw an error. Here is an example. Work by yourself to see if you can use the grammar rules to construct the entire set of string accepted by the language. Note that an epsilon in the production rule means the non-terminal will derive into nothing, and a pipe means the non-terminal can use this production rule or this production rule. We're not going in depth into parsing techniques because there are many of them and they are very complicated. But here I'll provide a way to understand grammar in a top-down parsing fashion. But note that this is not how top-down parsers work, let alone bottom-up parsers. However, it should give you hopefully a basic idea how to work with Yacc. This is an example of grammar that accepts bash commands and any number of arguments. The token returned by our Lex is here. The input is listed above. The rules are also numbered. Our starting symbol goal will derive into non-terminal command and arguments, where command and argument will derive into command word and argument list. The command word can derive into one word, which will match the first word, the command of our bash input. Next, we have argument list, which has two production rules. Yacc sees that there are words left to match, hence it chooses the first rule and not the epsilon. Then we have another argument to match, so argument list derives the first rule again. Now we have finished matching the input, and we have a non-terminal left over. Hence, Yacc chooses the epsilon rule to get rid of the last non-terminal, and our parsing is complete. Here is another example. Try to parse this input on your own. This should be a lot simpler than the first example. This concludes the introduction to Lex and Yacc. Hopefully you have learned something from this video. Keep in mind that this is a very introductory video, and I will leave a roadmap of parsing techniques for those who are interested in Yacc. Thank you for watching.